Okay. So today we're going to look at the, so I've mentioned it a couple of times, the law of quadratic reciprocity. We'll talk about the computer now in a second. So just to remind you, make it quick, what we're talking about. We've got our Legendre symbols. NP plus 1 if n a quadratic residue, sorry that's worse, a quadratic residue mod p. It's minus 1 if n is not a quadratic residue mod. And as a way of introducing the law of quadratic reciprocity and kind of encountering what it is, we pose ourselves the general problem of evaluating NP. Given an n, given a p, is n a quadratic residue mod p? Is it not? And what we seek is a nice, kind of sophisticated way to answer that. Some nice systematic way we can answer that. Okay? So now, from the fundamental theorem of arithmetic, we of course the natural way to think of an integer in general is to think of it in terms of its prime factorization. Okay, any integer n can have a thing like this. Okay, and there's essentially writing n as a product of primes. So we got distinct primes pi. A certain number of them are, so there's P1, P2 up to PR are the prime divisors of n, and each of them occurs with a certain multiplicity in the factorization of n, with the exponent alpha I. So when we think about the Legendre symbol NP, we think of it as the Legendre symbol of n, but now thinking very much of n in terms of its prime factorization. And we've already proved in some of our initial investigations into the concept of quadratic residues, we proved that the Legendre symbol, if you think that the prime, the prime that you're using as a modulus, this thing is a multiplicative function on the first argument. Multiplicative function of, well, let's stick the n in there. Whatever's in the first argument, the Legendre symbol of that number, it's a multiplicative function. So here you've just got a big product representing n. So this reduces to the individual Legendre symbols, taking the product of them all from I equals 1 to r and raising each one to the power alpha I. So you get that from just applying the multiplicative property of this function. At its most basic level, it just means that the Legendre symbol of n times m mod p is the product of the two Legendre symbols. That's what being multiplicative means. It's completely multiplicative. Sorry, yeah, in the number theory sense, remember we introduced before, multiplicative just requires that it only has to work when the arguments are coprime, the two factors are coprime. Actually, it's completely multiplicative. So the arguments don't have to be coprime. Completely multiplicative. So is everybody okay with that move? Yeah. Factorizing n, and that allows you to factorize the Legendre. We've proved it's multiplicative. So you see there how the general problem reduces to the problem of evaluating Legendre symbols on primes. So if we can understand some kind of somehow understand PQ for primes P and Q, so I'm departing from the the specific meaning of P1, P2, P3 up to in the prime factorization of n. Now I'm just posing the general problem. Can we understand the Legendre symbol of one prime modulo another prime? Okay? Because that's the kind of thing we have featuring here. Okay? If we could figure out all these values, then we could just multiply them all together, then we could figure out the value for n. So if we can understand the Legendre symbol PQ for primes P and Q, we can understand, via the fundamental theorem of arithmetic, we can understand how to evaluate general Legendre symbols. So now our general problem becomes this one. How does PQ behave? The Legendre symbol of P modulo Q behave? We know, given any two primes, it's going to be +1 or -1. Either the prime P is a quadratic residue modulo Q, or it isn't. So this takes the value +1 or -1. Okay, we won't sit here trying to meditate on it, asking ourselves how does it behave. We'll actually go and look. Okay, we'll look at a whole bunch of primes, and we'll calculate these values using the computer. How the computer does it is a bit of a moot question. We might further investigate that. How the code that we're about to look at, how exactly does the function work to answer these questions? That might be interesting to look at. But for now, we'll just take it as a magic black box that the computer can give us these values. But we want to look at them and see if there's any patterns there. Okay. Any questions just about that setup, about that? Okay. Key thing to understand is we have this general problem of determining whether n is a square modulo p, whether it's a quadratic residue mod p. Through the fact that we've introduced this notation of the Legendre symbol, we've proved it's multiplicative. That means we can reduce the general question to understanding how one prime behaves modulo, whether it's a square or not. Okay, so let's have a look at this. I'm going to go back to sharing my screen. And I want to go to the computer. Let me go there. Wait, where's it gone? Where has it gone? There's it gone. Okay, here we go. Okay, so this is some Sage map code for this. So we're going to draw a couple of pictures. So the first picture here is just introduced here. We're going to look at all the Legendre symbols PQ, and we're going to draw a blue dot if it's +1 and a red dot if it's -1. Okay. Now, what do we mean by that? Well, let's just have a look at this code, how it works. N is 200. You see here, I'm talking about primes 3 to n. So this command primes 3 to n produces it's called an iterator in Python, but it's just something that represents all the prime numbers between 3 and n. So we're going between 3 and 200. G is set to be graphics empty brackets. That gives you an empty graphics object to which you can add. It's like an empty canvas to which you can add graphics elements. I set up a load of points. So we're going to look at these pairs of primes, P and Q, as points on the two-dimensional plane, two-dimensional grid. Yeah, so P is going to be the horizontal axis because it's the first entry in the vector, and Q is the vertical axis. Yeah. So points is this big list. So the square brackets on the outside. It's a big list of every pair PQ, where P is something from the primes between 3 and n. Q is also something from the primes between 3 and n. And we're just cutting out, we're not considering the cases of the prime equal, where P is equal to Q, because then P is congruent to 0 mod Q. We don't really speak of, 0 is always 0 squared. It's not particularly interesting as a square to look at. Okay? So we're looking at every pair PQ, where P and Q are different between 3 and 200. And what does the code do? Well, if the Legendre symbol is an inbuilt function in Sage, it evaluates the Legendre symbol, just like we've been writing. So for every x in points, so x in this for loop is one of these pairs, PQ. X0 refers to the first element, X1 refers to the second element. Remember, in most computer languages, array indexing begins at 0. In MATLAB, it begins at 1. But most other computer languages begin indexing at 0. So so this essentially says if the Legendre symbol PQ equals 1, we add to G, so G plus equals says add to G, it's shorthand for G equals G plus whatever, and we're adding a point at location, the X vector, and we're coloring it blue. So blue for when the Legendre symbol is +1. Otherwise, else, by implication, the Legendre symbol will be -1. If it isn't +1, it has to be -1. So we'll plot at that point X a red dot, okay? So this will allow us to quickly visualize what's going on with the Legendre symbols PQ. So the for loop runs pretty quickly. The slow bit is just generating the plot, just kind of constructing the image. And I'll expand that out a bit just to look at. So what was it? It was blue. What was it? Blue was +1 and red was -1. So the blue dots, a blue dot means that P, the X coordinate, is a quadratic residue modulo Q, the Y coordinate. And a red dot means it's not a quadratic residue. Okay, it looks pretty. It acts as expected in the fact that, you know, it looks like there's roughly half as many blue dots as red dots. That makes sense, because remember, we've already proved that for any particular prime, half of the congruence classes are quadratic residues, half aren't. There's this 50-50 distribution in any particular modulus of quadratic residues and quadratic non-residues. So we look at a whole spread of residues with respect to different moduli. It's good to see that roughly 50-50 pattern emerging. If we fix a certain prime, let's fix a certain prime. So just above 100 is 101. So that column that the mouse pointer is under, just to the right of the tick at 100, that's the prime P equals 101. So above that, you see the first red dot is saying that the prime 3, because that's the dot start at Q equals 3 on the x-axis. So that red dot there is saying that 3 is not a quadratic residue modulo 101. The blue dot above it says that 5 is a quadratic residue, 7 isn't, 11 isn't, 13 is, 17 is, 19 is, and so on. Now, aside from the roughly 50-50 distribution, looking in any particular row or column, it's hard to discern any pattern. The occurrence of the red and blue dots, I would say, I mean, no immediate pattern leaps out to me, other than they seem to be occurring with, on average, 50-50. You just look up any particular column or across any particular row. It seems to be roughly 50-50. So it's not as if any amazing conjectures are leaping out at us looking at a particular column or a particular row. We already know about, we've already proved the 50-50 split between residues and non. But a natural question to ask is, what's the symmetry in this picture? Is there any symmetry in this picture? Okay. So you can kind of see the gap, the kind of P equals Q gap. Because remember, we didn't generate the points for when the prime P was equal to the prime Q. You can kind of see that as a gap in the 45-degree gap. So across that, in reflection across that, is there any symmetries that we may spot or may become aware of? It's tempting to ask, is the plot symmetrical around that? Now, it's not as easy as that, okay, unfortunately. If you look right down the bottom left corner, you see you've got a little arrangement of 3 reds up here. We've got red, red, blue here. So it's certainly not completely symmetric. And you'll spot many other differences up here. So the bottom right-hand dot down here is a blue. The top left-hand dot is a red. However, if you inspect columns and rows, okay, so when you reflect, say this last column down here, when you reflect in the line, in the 45-degree line, that last column becomes the top row. Yeah, That's how reflection works. So compare the last column with the top row. They're not the same. These reds are the same, those blues are the same, but then you got a red here and you got a blue here. So those two aren't the same. However, if you look at the second last column, under reflection, that goes to the second highest row. Yeah. If you track the blue and red dots there, you see they are exactly the same. Starting from the bottom on the second last column, it goes red, red, blue, red, 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 blue, blue, blue. Reading across the second top row, it goes red, red, blue, red, 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 blue, blue, blue. Okay, just exactly the same. And it continues up. So the second last column is exactly the same as the top, the second top row. It's reflection. You might look at a few more. Look at these next, the fourth and third last columns above the mouse pointer there. Are they the same? The third last one goes blue, red, and then four reds. No, that's not the same. Oh, no, it is. Blue, red, blue, four reds, blue. So some of the rows are symmetrical with their columns. Some of them aren't. That's a bit weird. Now, this picture, if we're investigating this question of symmetry, right, we're not so much interested in whether any particular dot is a +1 or a -1. Now we're interested in, is the symmetric? Is the same residue status, is it the same residue status of P modulo Q as it is Q modulo P, which is the reflected? Yeah. PQ is a point in the lower triangle, QP is its reflected point in the upper left triangle. So we can generate a second plot. So we're not keeping track of the +1s and -1s. Now we're going to keep track of whether PQ is equal to QP. So we slightly modify the code. So this time we're going to draw dots at the locations PQ, but now we're going to do an unfilled circle for equal. I'll get rid of the red and blue is a bit garish and distracting. An unfilled circle for equal status and a filled circle for unequal status. Okay, so the code is structured quite similarly. In the for loop, we calculate the two Legendre values, and we calculate the two Legendre values and as L1, L2. So L1 is P mod Q, L2 is the other way around, Q mod P. And if L1 is equal to L2, we stick an unfilled circle, because we've got fill equals false. If L1 is equal to minus L2, the second part of the if statement, we do a filled circle, fill equals true. Okay, and we get this nice plot here. I've reproduced copies of this, so I want us to inspect it a bit closely. So I'll do that too. So this is the plot we get. So let's switch to, or any questions, first of all, about the code or the use of it. I'll share this worksheet. I'll put this worksheet as a link into the video description as well. So if you want to go on to CoCalc and experiment with this code, investigate other ranges of primes and so on, I'll provide the link. Okay, so you got your p-axis, you got your q-axis. A empty circle. So this picture is symmetric, right? That's clear. The pattern of red and black dots is symmetric across the diagonal, but that's the way it was constructed, right? Because a white dot means that PQ is the same as QP. Okay? So the black and white dots do not mean is a residue, is not a residue. They mean has the same status, right? So if it's a white dot at any certain location, it means that PQ has the same status as QP. If P is a quadratic residue mod Q, then Q is a quadratic residue. Or they're both non-residues. They're either both residues mod each other or both non-residues. The black dot, as there is in the bottom right-hand corner and the top left corner, because remember this picture is by definition symmetrical. But the black dot means that the PQ here, well, it either is or isn't a residue. I don't know. I can't remember the blue or the red that it was. But whatever status this bottom right-hand one has, whatever status that P has modulo that Q, the Q mod P is the opposite status.
So what's going on here? First of all, remember, from inspecting the other picture, we did see that some columns were the same under reflection.
So that's repeated here because you see that some column is all white. And of course, under reflection, that goes to a row that is all white. Okay. This row here is all white. Under reflection, it goes to this column here, which is all white. There are no column or rows that are all black. The blacks occur in columns or rows, and it's a mixture of whites and blacks.
And if you look in one of those columns where there are black, where it is a mixture of blacks and whites, you see it's roughly 50-50. Again.
It's interesting to see here, there's a large gap between the primes just after 100 here. It's kind of interesting.
What's going on? Can we see the pattern in the black and white dots? Is there one? And can we see what it is?
Now remember, these primes, where are the dots? We're just drawing dots at all odd values. So that first column is the prime 3, the second column is the prime 5, then 7. Then there's a gap until you get to 11. Yeah?
So the circles are located at the odd integers. And we're only seeing circles at the prime odd integers.
So circles are not plotted at the odd integers that are composite. So we see either a black or a white circle at the prime odd integers. But if you start counting, if you start stepping through the plot, but just step through all of the odd integers, okay? And just look what the pattern is. So column 3, you've got a mixture. Column 5 is all white. Column 7, you've got a mixture. Column 9, if it was shown, but it's not prime, but let's just call that white, all white. Column 11 is a mixture. Column 13 is all white. Column 15, it's not prime, let's call it mixture. Column 17 is all white. Now, how am I saying my all whites are mixtures? I'm simply alternating. So that's a conjecture that okay, we only see them at every prime location, but if we just assign to every odd integer the label all white, mixture, all white, mixture, they just alternate as you step through the odd integers. And that's exactly replicated, that pattern. Okay, look at the end. Here you've got mixture, all white, mixture, all white, mixture. Yeah. So one part of the pattern looking at the odd integer positions, the columns, or equivalently rows, remember the picture is by design, it's symmetric, so it's talking about status across the diagonal. Looking at the odd integer positions, the columns and rows alternate alternate as all white mixture. All white mixture, all white mixture, all white mixture. That's preserved in this sample up to 200. It's a reasonable conjecture. Okay? By no means a proof that that pattern is there, but it's strong, well, it's suggestive evidence. Let's look along a mixture row, or equivalently, look up a mixture column. So pick one of the columns, which is a mixture of black and white dots, and ask yourself, how are the black and white dots occurring along that row? And again, if you look at what the classification is, as if you're stepping through every odd integer position, not just the primes, but actually just step through the odd integer positions and start pulling out white or black as you go up the mixture column. So let's choose the last one. It's easy to pick out. So the last column. It's black, white, black. Okay, then we skip an odd integer and go to black again. And then white. Then we skip the odd integer and go to white again. Because we're skipping the composite numbers, we're only showing prime numbers. But if we just start, see is there a pattern as you go through all odd integers? Black. So I'm going to count up the last column, just saying something for every odd integer. It goes black, white, 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 black. And the pattern is obeyed. Okay. We only see the circle at the prime positions, but if we label every odd integer position as black or white, the colors match when they are shown for the prime position. So looking along a mixture row column at all the odd integer positions, we only see the circles of the prime positions. At all the odd integer positions, the labels white, black, again alternate, seem to alternate. They do alternate in this picture, which is just the primes up to 200, the odd primes up to 200. So we might conjecture that they always alternate. Remember, there's an infinite number of primes, so we can't settle this question just purely by looking at samples and looking for patterns, but it is quite suggestive. So what we're seeing there is the law of quadratic reciprocity. Now we'll give it a much nicer formulation now in a second. Okay? So this word reciprocity, reciprocal, it refers, it's this me to you, you to me idea. Reciprocal. Reciprocal violence, they talk about sometimes. Revenge and whatnot. Reciprocity. So how do we encode it? Well, this alternating stuff, well, that suggests modulo 2 behavior, right? Alternate 0, 1, 0, 1, 0, 1. However, what we're seeing is, remember, we've cut out completely from this picture all the even integers. The circles are only, because they're located at odd prime positions, the circles are only at odd lattice points, odd coordinates. So what we're talking about is stuff that's alternating across the odd integers. So if we're speaking of a pattern that's alternating across the odd integers, really, I think we're talking about modulo 4. Because we got a repeating pattern, yes, no, yes, no, yes, no, but only across the odd integers. So really, we want to talk about all integers. I think we're talking modulo 4. So patterns that alternate across odd integers suggest modulo 4 description. And this is the law of quadratic reciprocity. This is the way it's normally stated. It's stated about the Legendre symbol PQ. And we're interested in whether it is equal to QP or has the opposite sign of QP. So remember, this is not telling us whether one is a quadratic residue modulo the other one or not. This is telling us whether they have equal status modulo each other or opposite status. So it's one of these. So when is it opposite status? So we see opposite status beginning at the prime 3. We see it's possible to have opposite status beginning at the prime 3. We can have it at the prime p equals 7. You see, and then it alternates then. So we get the prime 3, and then it alternates and we go to 7. And then it goes to 11. So because we're skipping one status, but we're only moving across the odd integers, these are all the primes congruent to 3 mod 4. Now this description isn't finished yet. But at all the primes p that are congruent to 3 modulo 4, we do see, in that column, we see a mixture. Okay. But it's a mixture of white and black dots. White means the same status, black means opposite status. So I'm trying to describe here the opposite status. So if you take the column 7, for instance, what kind of, when does the opposite status happen? Well, it happens with q equals 3. And then it's going to alternate across the odd integers. It next happens at, it doesn't happen at 5, 7 we're not considering, it doesn't happen at 9 isn't prime, but it again happens at 11. Not at 13, skip 15, not at 17, but again at 19. Okay. Now what's happening there? You see there we're stepping distance 8 each time. So again, it's whenever q is congruent to 3 mod 4. And q is congruent to 3 mod 4. So when both p and q are congruent to 3 mod 4, it appears that they have opposite status. And the white dots are at every other location. So at all other locations, if at least one of p and q is not congruent to 3 mod 4, then they have equal status. Remember, every odd prime is either congruent to 1 or 3 mod 4. Primes can't be congruent to 0 or 2, then they need to, except for the first prime, 2, but that isn't in this picture. Okay, so this is the law of quadratic reciprocity. I'm still coming to terms with this, really. I'm still trying to improve my intuition about it. People describe it as like one of the, I mean, it seems obvious now that you're looking at the pattern, but people just talk about it as the kind of result that, wasn't expected. In our study of modular arithmetic, when you study prime numbers and you introduce the idea of modular arithmetic, you think about squaring. It does come as a bit of a surprise that there is this very easy to describe when the relationship is the same and when it isn't. Because it seems to be hard to describe what the intuitive evidence or, any kind of simple, kind of easy to digest reason why this should be true. And we do have a proof of it in the book, a couple of lemmas and then the final proof. I'll discuss that probably next week or that. But what I want to show, now I've only got 10 minutes left, but what I want to show is immediately show some of the power of the law of quadratic reciprocity. Some of its power with a nice application of it. So any questions about the statement of the law? So we're still in the, given a certain prime, given a certain pair of primes p and q, still a little bit in the dark about how to work out if it is a quadratic residue modulo the other.
but we can easily work it. If you give me gigantic primes, but if you tell me all their digits, I can immediately tell if they have the same status modulo one another or opposite status. Because I only just have to figure out what they're congruent to mod 4. And no matter how big the number, if you have all its digits, you only have to look at the smallest 2 digits to work out what it is modulo 4, because everything else is a multiple of 100. And 100 is 0 mod 4, then it's plus the tens and units. So it just comes down to the tens and units, what they are modulo 4. So let's look at an example, which I think is one of the exercises from the end of chapter exercises. Using the law of quadratic reciprocity, we get an algorithm for evaluating Legendre symbols. It's not immediately obvious, but the law of quadratic reciprocity allows us to flip Legendre symbols. Factorize, flip, reduce. 3-step algorithm. Factorize the Legendre symbol. Factorize the n in n mod p. Fully factorize it, like we showed before, into its prime factorization, and factorize the n in n mod p, and then factorize the Legendre symbol itself as the product of the other Legendre symbols featuring primes. Then flip PQ, flip it to QP, and it's either plus or minus QP, and whether it's a plus or a minus, the law of quadratic reciprocity tells you. It tells you whether you need a minus sign when you flip the Legendre symbol. Now you see, typically, when we're trying to calculate a Legendre symbol, typically we've got a small prime modulo a big prime. So when you flip it, you're then looking at a big prime modulo a small prime. So reduce means reduce the n in NP to its smallest representative modulo P. Okay, the best thing to do is just to dive in and show you an example, and you'll get a feel for what it is. But it's factorize, flip, reduce, factorize, flip, reduce, factorize, flip, reduce. Now, is this process going to go on forever? Factorize, flip, reduce, factorize, flip, reduce. If you were just factorizing and flipping, it might go on forever. But what in this bit tells you is going to stop. I mean, you can flip things till the cows come home. You probably factorize them until the cows come home as well. But you can't reduce things forever. If we're evaluating these on positive integers and we're reducing them, eventually we run up against the wall of 0. So it will stop in a finite number of steps, just like Euclidean algorithm. Remember we did the Euclidean algorithm where you had to work out the GCD of large numbers. You did an integer division, you got a slightly smaller remainder maybe than what you did, than one of the numbers. You then looked at the GCD of that small remainder and the not so big one from the original pair, or the big one, whatever it was. Yeah. And then you repeated that process, and the numbers were getting smaller all the time until eventually they're going to get so small that it was obvious what the GCD was. Exactly the same here. So the task here will be to evaluate 461 modulo 773, just a complete example. So these are both prime. So 461 and 773 both prime. So there's no factorization to do at the start, because 461 is prime. You can't factorize it anymore. So we will flip it. What's next? Using the law of quadratic reciprocity. Well, we can flip it. It becomes 773, 461, but we may need a minus sign in front of it, just according to the law of quadratic reciprocity. So we just have to test these, see if they're congruent to, if both of them are congruent to 3 mod 4, then we will need a minus sign.
But 461 is not. 461 is congruent to 1 mod 4. Remember, you only look at the 60 and the 1. 60 is congruent to 0 mod 4. It's 4 times 15. That's congruent to 1 mod 4. Okay. So that's by the law of quadratic reciprocity. We flipped it, we reduce it. You see, we're asking ourselves, is the congruence class 773, is that a quadratic residue modulo 461? Well, we're complicating things. What is the congruence class of 773? It's got a simpler representative modulo 461. So you divide it by 461 and look at the remainder, it's 312. 773 is 461. So that's justified because 773 is congruent to 3112 modulo 461. 3112 is certainly not prime. We can factorize it. 3112, the factorization is 8 by 3 by 13, apparently. 8 by 3 is 24, 24 by 13. So this Legendre symbol factorizes into 2, 461 cubed, 3, 461, and 13, 461. Okay, now we go, oh my God, we got 3 Legendre symbols to work out. What am I doing? At the start, we only had 1. But notice these are simpler Legendre symbols in the sense that their arguments are smaller. The first Legendre symbol was modulo 773. Okay, we've got to figure out 3 of them now, but they're modulo 461. It's an easier task, so to speak. It's got smaller arguments, a smaller system. Instead of modulo 773, we're talking about modulo 461. Now, we proved a whole lemma about the status of 2. It was lemma, the consequence of Euler's criterion, theorem 8.6. So by theorem 8.6, we know what the status of 2 modulo 461 is. It just comes down to the status of 461 modulo 8. It's minus 1. Okay, so what is 461 modulo 8? So that's true since 461, so divide that by 8, 8 into 40 goes 1 to the remainder 6, 8 into 61 goes 7 times 56 remainder. Yeah, 5. So since 461 is congruent to 5, which is congruent to, think of that as minus 3 mod 8. And so by theorem 8.6. Theorem 8.6 said when the prime is congruent to 3 modulo 8, or minus 3, and 5 modulo 8, 2 is not a quadratic residue. We don't know about 3s yet, we don't know about 13s. So we did factorize, flip, reduce. So we go back to factorize. No, we did flip and reduce. No, what did we do? We did flip, reduce, and then we did factorize. So we're back to flipping again. Yeah. So we flipped this. So this is 461 mod 3. That should be easy. And 461 mod 13. Yeah. Okay, minus 1 cubed is minus. 461, well, okay, we just flipped. Now we reduce. What is 461 modulo 3? It's 2 modulo 3. And 461 mod 13 is 6 modulo 13. So that's true since 461 is congruent to 2 mod 3, and it's 461 is congruent to 6 mod 13. Tiny Legendre symbols. You should be able to answer these quite quickly. Is 2 a quadratic residue modulo 3? Modulo 3, there are only 2 things, 1 and 2. Half of them must be quadratic residues, that is the 1. So 1 is a quadratic residue mod 3, 2 is 2. So 2 is not a quadratic residue. So this is minus 1. 6 factorizes as 2, 13. 313. Okay, minus minus, that's a plus. 213, we answer with 8.6. 213 is, well, what is 13 modulo 8 is congruent to 5. So that's a minus. So those two minus, well, let's just repeat them in so we can keep track of what's happening. 213 is a minus 1. 13 mod 3, we can flip. So this theorem 8.6 for 213 equals minus 1. Okay, because the prime is congruent to 5 mod 8. So we got 3 minus signs, we got a minus sign. Reduce 13 modulo 3, what is it? 1, 3. Is 1 a quadratic residue modulo 3? Yeah. Okay, 1 is 1 squared. So it's minus plus 1. So in other words, it's minus 1. What is minus 1? This thing we started with. 4, 6, 1, 7, 7, 3. So apparently 4, 6, 1 is not a quadratic residue. Modulo 773. So a couple of days ago, or a few lectures ago, we had this general question of how do we work out n mod p, the Legendre symbol n mod p. We could only answer it with the very basic, naive brute force calculation method of, we'll just square everything modulo p and see if n occurs. But that's like using a shotgun to, I'll talk about guns. But it's a unsophisticated method. You just have to inspect everything and see if your thing is a quadratic residue. This is much more sophisticated. We're making use, the crucial ingredient here, well, every ingredient is crucial, but the law of quadratic reciprocity really makes a difference because it allows you to flip it, which then allows you to reduce it. And reducing it gives you this algorithm thing. You can reduce complicated questions to simpler questions. And it seems very reminiscent to me of the Euclidean algorithm. Taking a question about large inputs, reducing until it's a similar question about small inputs, which you can answer trivially. That's a very similar idea. Okay, we'll be discussing quadratic reciprocity a fair bit, and we'll look at other applications of it, other significant properties that it has. Okay, so I'll see you tomorrow for more of this.